certain molecules. It could be something that your olfactory organs can sense. Okay, you have more of this here. It could be a very nice perfume perhaps, and less of that. So I spray it 15 times here, and someone sprays it 2 times there, right? So you have these molecules, and your nose is not a very poor sensor. It can more or less sense. And I'm kind of standing in the middle. So if I turn my head to the left, I see, I can sense less. If I turn to the right, I sense more. But I let time pass, okay? And after about, say, half an hour, it looks like, no matter which way I turn, I can get the same strength in terms of what I smell, okay? So what is your feeling? Are these molecules, the ones where there's more, are they traveling faster? Or is it those molecules that are, it's those molecules which are somehow attracted to these higher concentration and hence they're moving this way? Or vice versa, or something in between? What's going on? Is the diffusion coefficient of individual molecules the same or not the same?
Same.
They are the same, please understand. Diffusion coefficient is coming from the tendency to move over. And that is determined by A, temperature, the viscosity, the viscous friction coefficient, and also the size of the molecule. In that A, in that radius, that size is important. Okay. But what you are effectively counting is the number of molecules flowing per unit area per unit time. So if I keep a tiny area here, okay, I take a small, piece of board or something, say 10 centimeter by 10 centimeter, and I face it this way, how many are crossing my little area per unit time? And I face this way, how many are crossing per unit area per unit time? That will give it. So there will be a net movement simply because there are more molecules there. So please do not get confused between flux and diffusivity. Okay, your flux J has the diffusivity when you calculate the flux from Fick's equation. Okay, as we'll go into the next slide, the D is there, but there's simply a large number of random events going on. If I touch this is so sensitive. If I touch this, I lose my slides.
टच करने से आता है ना जो टच करने से ऐसे
Sorry, I'll have to get an extra class.
एक्स्ट्रा क्लास क्या नहीं भाई.
Going to it, please pull down the two flux equations that we have, right? Fick's equation rather. There were 2 equations. What was the most important difference between the 2 Fick's equations?
First derivative second. There is second order in the second equation is second order differential equation.
Go to the first one.
First one is first order differential equation.
First order differential equation. What is not there in the first one?
Concentration with respect to time.
There's no time in the first fixed equation. J equal to minus D del C del X. Okay? So we are doing it with as simple calculus as possible, but del C del S is the gradient of the concentration. So if I have a concentration gradient, it will determine my flux. Please remember, flux in any physics, in any biology, in any chemistry is number per unit area per unit time. Okay? So there's a minus sign there, D. Okay? So it's, it goes with the negative gradient of the concentration. But when you go to a unfortunately, I won't be able to write on the slides. I really hope to do that. Alright. But in the second flux equation, you also have time. Okay? And as you said, there's a second derivative. What is the second spatial derivative? Can anybody, I don't expect you to know, but does anybody remember? What
Laplacian.
Huh?
Laplacian.
It's a Laplacian, but forget about fancy things. When I'm just looking at some function in space, who said? It is a curvature. The first derivative is the slope, second derivative is the curvature. It is how your slope is changing. It is the rate of change of slope, right? So with that, oh now this is fine, then good. So we'll look into those considerations today. But before we do that, quickly, this is the regime that we have been taught, right? It is when, diffusion, when your R square is a linear function of the time elapsed, and the proportionality constant gives you, there's dimensionality of the space within there, there's a diffusion coefficient within there. Some cases, I just want to highlight, you won't pay attention to these, but once in a while, these are old slides, I had updated the slides in the iPad. But, sometimes you will have R square exceeding the straight line or R square dipping below the straight line. Those are anomalous diffusion, and those happen because it's not purely a random walk. I had it, I'll share the slides in the iPad. These are not, really random walks, there's some bias there. And, very frequently you'll encounter these. I'm just pointing out, you will not, those are much more complicated theories, we will not get into that. But if I simply look at this, again there's some problem here. There are two Einstein relationships that we have looked at. Okay, and this introduces how much thermal energy is there. Okay, so please, look at all the relationships that involve D, diffusion coefficient, and twist them around. What are the factors that are coming into play when you're looking at the diffusion coefficient? We had done this, so we will not do the derivation again. Okay, so we have two equations as we just said. I'm sorry that some of that part is missing. Okay, there's an alignment issue. Alright. So there's a del C by del P. Now, let us look at these cases. So again, this is missing from this version of the lecture. So we can have, very broadly speaking, two kinds of cases. One is steady state. You remember steady state that we discussed, much earlier in the classes. What is steady state? When something does not change with time, it is not necessarily equilibrium.
Dynamic equilibrium.
Something is maintained. Okay. So perhaps let's assume the simplest steady state concentration condition where this is uniform. Okay. You can simply think of it as just think of a beaker full of salt, for example. Simplistic level. Okay, it's uniform. And if I'm kind of drawing an X line, it's uniform all over there, right? So if I do that. Okay, will there be a flux? No. Why? Because my concentration does not change with space. Del C del X is equal to 0. Okay, there will not, even if you look at the second one also, del C del T will also not change, right? Same here. Okay, so I'll just go same here. Just how this is happening, steady state conditions. Maybe there's a continuous emission of some particles, or there's this organism is kind of synthesizing something. So it's kind of maintained. In this case, because this part is 0, this is not going to change with time. However, we had, I'm so sorry, these are all mixed up. We had looked at this case, okay? So how do you imagine this case? So imagine that you have done these diffusion equations, but imagine I have this big beaker, and at some point, I inject a set of molecules, or maybe they're colored. Okay. So if I inject that, okay, and I'm only doing a one-time injection, okay, at x equal to 0. How is that concentration profile going to spread? So if I let it spread, because it's unbiased random walk on each ends, if I only look at x, it's going to have this kind of a profile. But what will determine its profile down the line? Okay, so remember, I'm going to look at del 2c by del x squared. In other words, I'm going to look at the curvature. What is the curvature at the topmost point? It's a negative curvature. We call this negative curvature. What is the curvature here? 0. At that particular point in, those are known as, anybody? Inflection points. That is where at inflection points curvature works from minus to plus. So exactly at the inflection point, your del 2c by del x is equal to 0. Okay? And now here at the scale end, So the curvature is positive. So if you just characterize the nature of the curvature, it will tell you how is del C by del T positive or negative. Get it? So, this broken line is the future profile. Okay? So here, why does it not change over here? Because the curvature of the concentration distribution is 0 at the inflection point. Get it? This might seem very trivial, but this is actually a very handy concept. So I have something which is a bit more advanced, and I don't expect people to kind of go through this. So imagine again that there is some kind of a cycle. Okay? So let's say your organism, for whatever it is worth, it is kind of generating some effluxes, okay, over time. Alright? And you kind of, you look at the data and you see that your concentration profile fits something like this. So at time t equal to 0, okay, you have C bar and it goes on like that. At time t equal to 0, you will have that exponential will be 1, right?
1.
So you will have a sinusoidal time profile. As I am going further in time, there will be a sine plus something like this. So, if you are not interested in this particular slide, it's okay. But I just want you to know that if I have a concentration profile like this, there's a little exercise that I recommend that you do. Fit it into the fixed second equation and see if this satisfies your del C by del T. Okay? So, these are some more complicated cases where you will have concentration profiles migrating as a function of time. And if you just know which way your curvature will change, that will help you identify if your concentration is going to go up or go down. Okay.
Last class when you were doing this, there was a problem that you didn't understand.
Which one was, I think what I remember that. What we did not say, I think one thing I missed out saying, is consider these as steady state cases. I did not mention the word steady state. Okay, so if you just use the condition steady state. Now, who is giving that steady state concentration? That is a separate question. But if you have that steady state, okay, then you can look at the slope and the curvature of your concentration profiles and predict how it will change.
If I have a gradient that is in a steady state, it won't change.
Yeah, then your flux will be 0. If I maintain the steady state, in this case, okay, where the concentration profile is like that.
So only this particular one is in steady state, not the Gaussian one.
Not the Gaussian. So today I had subheadings saying non-steady state conditions and steady state conditions. I'll share those slides with you. It is there in my iPad. Okay. So these are rough slides which I have in my. Okay. Look at this also. For those of you who are not challenged by math, you can look at this, but I will not give this to you in an exam or anything. This is just to make the concept a bit more clear. Okay? We have both time and space dependence of concentration. Alright. So here what we actually end up with, so you see again time. So you can say time 1, time 2, time 3. I have some concentration here, some concentration here, and the molecules have been tagged as grey and black. Okay, and let's say they intermingle. So same here. Let's say I had colored molecules. I had chlorine and something else of colorless thing. You would actually be able to use your sight as well, other than your olfactory senses to identify. Right? Now the question is, many times in biology you do not want that. You want to maintain the concentration. Can you think of a scenario where concentration needs to be maintained? Simple scenario, yes. Inside cells, you have to maintain turgidity. You have to maintain a certain amount of concentration of your cells. What if my cells are all mixed up? See, a cell is a special compartment with a lot of concentration gradients, right? If you don't maintain that, then life will actually not work, right? So we are going to, in this class, we look at 3 ways in which you can actually maintain the gradient. Okay? One will be electrostatic potential, and those of you who talked of ions across the cell membrane, you already perhaps are kind of hinting as to what we will be looking at. We'll look at gravity. Gravity is actually a weak force, much weaker than your electrostatic force, but in principle, if you have heavy particles, you can also have gravity, maintaining the concentration gradient. So for example, if I take, very fine sand particles, that is also trying to diffuse, right? But there's a gravitational effect which is kind of working against the diffusion. So even if I stir it hard, the gravity will work against the diffusion and set out. So, and the other thing is centrifugal force. Why is this important in biology? So this is an artificial condition, and those of you who have started going to some labs will realize that your PI will often ask you to centrifuge certain things, right? So if you just take your blood and subject it to a centrifuge, all the components, there will be a density gradient, and you can pick up, the parts that you are interested in, right? So let us look at the first one. Unfortunately, again, my iPad is not working, but let's consider a cell membrane, typically referred to as a plasma membrane, alright? So you typically have, a lot of concentration difference across it. And let's say your plasma membrane was completely permeable. What would happen? It is actually permeable to a large extent. For example, these hydrophobic, fat-soluble molecules, they can actually cross the membrane barrier. Okay? And what is the energy penalty they have to pay? That's a separate question. But then you have these channel proteins, okay, which selectively permit certain ions to cross from one end to the other. Okay. So what is required across membrane protein to maintain concentration gradients of, say, ions? You need a potential difference. Okay, it is a voltage difference. Okay, so the cell has to actually maintain a voltage difference to, say, have a different concentration of a certain ion here and a certain ion here, and we'll look at how to get that. Okay, we'll do a certain example. Alright, how to do that? Again, I don't want to go to the board. I will handwrite things and share the slides with you. So you have, I would appreciate it if you keep your conversations outside. It's very distracting and it doesn't help you or me. Alright? So look at this part. When I have said J subscript net, that is the effective flux. Okay? If I were to ignore this second part, then your first part is the first Fick's equation, Fick's diffusion law, right? I have put D here. Now let's say I'm doing something, I'm doing some work against the natural flow, and I'm offsetting that natural diffusion. So in other words, I have a flux in the opposite direction. Okay. Now this can arise from anything. It can arise from the three factors I just told you about. So let's say I'm actually applying an electric field, and I will look at a special case here where my particles have individual charges. If my particle is uncharged, then no matter what kind of electric field I apply, it won't respond, right? So I'm looking at a specific case where my particles of interest, the ones which would normally do some diffusion, have some charges in it. Okay? So if I consider, so again, imagine that there's a battery, okay, which is providing a potential difference of delta V. Okay, so the electric field across, and I consider a small box of length L, the electric field will be del V by N. This is very standard, your 10+2 electrostatics, nothing very complicated. Okay, the force on each charge will be what? The magnitude of the charge, I am looking at magnitudes only at this stage. Okay, magnitude of the charge times the electric field. Now the drift velocity is the overall velocity that is induced by the force. Okay, we are not going to go into too many details. It is the force, this force divided by the viscous friction coefficient. Okay, the full, very gory detailed derivation is there in Nelson, and if you want, I can take an extra class to describe all this. But you can actually define the drift velocity as this quantity. So instead of the viscous, so in the case of force, I'm going to write Q del V. So for force, I'm writing Q. And for this electric field, I'm writing del V by L. So you have Q del V by L times, the viscous friction coefficient. Now, if I define a small area A, okay, and I'm going to calculate the number of ions passing an area A, arbitrary area A in unit time delta T, what will that be? Dimensionally, this is fine. So at least that first order check will pass. It's the drift velocity times delta T times this, okay, so that is how much will cross this small distance, times the area times the ion concentration. I have just used the suffix ion because I am dealing with ion concentration. Okay, so J prime here will be N by the number per unit time per unit area. Okay, I told you, this is probably the 4th time I am telling you, flux is number per unit time per unit area. So if you get this, your extra flux is V drift times C ion, and you can work it out and it will come to a form like this. So I plug it all in, I get my effective flux as this. Now what do I want to do? I want to offset the flux. I want to ensure that there is no movement from one end to the other. So to offset that movement, I am applying a potential difference. So under that condition, what should my J be?
0.
J net or J?
0.
At the exactly offsetting conditions, what should my J be?
0. No?
0. Okay, so if I use, so that is called the Nernst-Planck formula, by the way. And when I put J equal to 0, when I offset this, so I am switching this to the left side, switching that to the right side. And please pay attention, del C by C, okay. Some of you might not be happy, I'm sometimes using partial derivatives, sometimes I'm using full derivatives, but those mathematical intricacies are something I would like to keep out. If I do this, I have integrated in the below, you have C, from top to bottom, that is the way this has been set up, okay, that is top, that is bottom. This is an integral equation. And if I integrate that, I'm going to get, what is the integral of dc by c? Log c. Okay, and if I put between limits, it's going to be, okay, delta of log c, which is log at the top minus log at the bottom, right? And the good thing about log, by now everybody knows, is if I have a difference of 2 logs, it is same as the log of the ratios. If I have addition of 2 logs is the log of the term. That's the beauty of logs. Okay. So if I get that, I will get an equilibrium relationship of this kind. I mean, this is where I'm kind of forcing an equilibrium to be maintained by applying a potential difference. So let us actually, so under such conditions, okay, so looking at the Nernst-Planck formula, and just imagine the plasma membrane. You actually have many kinds of ions on that side and this side. You might, I don't know if any of you had a grandparent or someone who kind of became dizzy because their sodium-potassium balance was mixed up, right? If you can run into serious problems if your ion concentration across your cell membrane is mixed up. So all the time, your channel proteins are actually maintaining that very specific voltage difference. Okay, and somehow if your C1, C2 or C top, C bottom does not exactly match your delta V, you're running into trouble. Okay, so here this is just a snapshot to show that what kind of voltage differences we are talking about. So let us actually do a more specific problem. So estimate the potential difference required to maintain a phosphate ion concentration. So phosphate would have a Q of what? Plus 3E, right? So minus 3E, right? PO4 3 minus. What is the charge of each? I'm talking of electronic charge obviously with the right sign. Okay, I don't want people to come back and tell me I don't know what the charge of a phosphate ion is. That is very, very elementary. And everybody knows the charge of an electron, I presume, right? If you have come this far. So what this system is trying to do is, there's a phosphate ion concentration by ATP hydrolysis and all the cycles that are going on. And on one side, I'm not discriminating, extracellular, intracellular for now. It's a very simple problem that we are picking up. I want to have a phosphate ion concentration which is 5 times on one side compared to the other side. Look, I'm not even telling what the phosphate ion concentration is. I'm only saying 5 times. So what is the advantage of this? I just need, so difference of log is log of the ratio. Difference of log is log of the ratio. If I have the ratio, I should be able to work this out. Okay? And I want you to try this. Okay, so I said 310 Kelvin. Alright? Note that this is kBT. If you go back to the formula, this is KT. So until and unless I give you the molar charge, charge per unit mole, in certain problems I can give you, the net charge per unit mole. Q molar. If I give you Q molar, then you can use RT as 0.6 kcal per mole or whatever it is. But in this case, if I'm using charge, if I'm using raw charges, I ought to use coulombs. Right? The safest bet for any calculation is to stick to SI units. It might be difficult, you might have to convert and reconvert, but that's a safe bet. It takes time, but many a time it's also true that in an exam you don't have that kind of time. So you need to be familiar with both these. So let us actually use our calculators and quickly find out what we are talking about here. So C2 by C1 is 5. So I'm going to have log of C2 by C1 equal to minus Q delta V by kT. So I'm going to do log of 5 equal to minus 3 into 1.6 into 10 to the power minus 19 times, if my delta be there, and this will be right?
So the formula will change.
Nothing to be frightened of. You have a large 10 to the power, very small 10 to the power minus 19 on top, and you have a 10 to the power minus 23. So, into 300 then. Excellent. So if you work this out, what does delta V come out to be? Of the order of. I want you guys to get a sense of what kind of voltage differences you have across your cell. So when I go to one of these plugs, I'm talking of 220 volts, right? When I'm talking of the potential difference across your cells, what order of magnitude are we talking about? This problem will give you a sense of what numbers we are talking about. Around 6 what? No.
0.014.
0.014?
Yeah.
Or is it 0.14? I thought
0.014.
yeah, 0.014 volts, right?
Yes.
That's true. So the answer is 0.014 volts. It's a little less than what the in millivolts, what is this going to be?
14.3.
14 approximately 14 millivolts. So if you ever end up in a physiology lab, electrophysiology lab to be more accurate, they will be talking about these values. Okay, it's typically millivolts. This is a little undervalued. So typically it's between 20 and 200 millivolts that we talk about. Okay, a typical electrophysiological voltage difference across cell membranes is between 20 and 200 millivolts. our numbers are within, closer to the lower values, okay? So there might be, a little bit of, it's probably not 5 times, it's a little bit more. If I just realize one thing, if I had 6 times or 8 times the concentration difference, would my delta V be higher or lower? Common sense tells me it has to be a stronger potential difference. Mathematically also, that should agree, right? Clear? So, so these are the takeaways from this kind of exercise. Of course, we will have situations where you have multiple ions. I have a lot of potassium on one side, a lot of sodium on the other side, calcium on one side, phosphate on the other side, chloride on the other side, right? That's a typical, it's very, very heterogeneous. And your cell is actually not doing this calculation. Your cell does not have a calculator, obviously. But it has to set the voltage. It all balances out in such a way such that your concentrations are maintained and your homeostasis, as we say, is amenable with homeostasis. Okay.
Once the Q we are using there, that is the net charge we need to maintain across the membrane?
No, you have to use the sign here. Okay.
Could you repeat what you said?
You have to use the sign here. So I used a charge of -3. If I revert the problem, so that is the thing with charges. When you look at a battery, you have to look at which side is plus, which side is minus. Try taking a wall clock and reverting the battery. It will fail. At the very least, it will fail. If your clock is not robust, it will go kaput, right? So you have to use the signs here. So that's a good question. I'll formulate some problems where if you use the wrong sign, you're going to, your numbers will try it with the wrong sign and see what you get.
What I was asking is, suppose we have like CO2 plus on one side and PO43 minus on other side. And we need to maintain, I don't know, what should we use? Do we use a net charge or what?
It's a good question. I'll get you a problem where you have, many charges. It's not a uniform charge. Okay, where you have when you have a mixture of charges and you're not only talking of C1, C2, you're talking of C1 prime, C2 prime, C3, so on and so forth. So I can add an index, a subscript I, that will give you the ion type. Okay, so your delta V, so the reality is that, you don't have a uniform delta V across all channels. So if you have multiple kinds of channels, okay, they're all working in tandem. So let's get to a more complicated problem. Based on this is an overly simplistic problem, I will. Okay?
Ma'am, in your slide, after slide, please, where you formulated the flux. No. In the derivation.
Okay, yeah.
Where you compute the flux, I am asking. J is equal to number of ions.
Oh, acha, where I put set that equal to 0.
That one.
Yeah.
So here you have written J dash is equal to N by A delta T. So
number per unit time per unit area.
So there the number of ions passing in an area A in time delta T. That is basically you have taken the number of ions. So in chemistry or anything, when we define a molarity or concentration of ion, so that should be number of moles of, right?
You can estimate it as moles.
So if we do it in moles, then we will get a different.
Sure, as I just said, you're absolutely right. You can reformulate these equations in molar terms. In that case, the advantage is you will end up with RT instead of K. So I may supply you, instead of number, I can supply you the number of moles. Okay, so this can certainly, I'm sure many textbooks have reformulated this, or many research papers are using the molar version. It is easy. Let's move forward. I'll go back to that. We have traveled quite a bit ahead, so that will be going backwards quite a bit. And I'm happy to discuss this. So in general, you realize that we can, generalize it this way. If I take ratio of the concentrations, I can use a force times a length by kT. So I'm not going to do rigorous derivations here, but when I'm using gravity, I'm going to use force as mg times h divided by kbt. And similarly, when I'm going to use a centrifugal force, okay, what is the centrifugal force if something is spinning with rotational velocity of omega? It's m omega squared r. But in a typical centrifuge, what is specified is rotations per minute. Okay, so if I have to do rotations per second, real angular velocity, I have to do divide by 3600. Okay. So if I use this formula, so let me just write this down. And I'm really sorry about not having the right slides up there. So let me write this out for you. Okay, so I'm going to say in the case of a centrifuge, we are going to end up with something like this. Let me try to draw one. So when you look at a centrifuge, what they actually have is an axis over which you are spinning. Okay? And then the centrifuge is placed a bit like this, not exactly laterally. Because otherwise, once you have spun it around, chances are it's going to fall back. But we are going to ignore this effect. But what you have is, if I'm looking at a distance r from the axis, log of the concentration at r by the concentration at 0. So this is r equal to 0. And this position is r equal to r, is m omega squared r times r by kbt. If I were to, if instead of omega, if I use rotations per minute, what I will effectively have is,
what are those two lines you have drawn? They're the two lines that you have drawn parallel.
So I was trying to draw a centrifugal tube. Got it? They are usually slanted a little bit. You don't want, I'm going to ignore that slant, so you can, if you work for a centrifuge company, you can make a lot of money in designing these centrifuges, okay, what is the, what are the values and all that, but simplifying it slightly, so let me write it down as, this whole comes down to 1 by kbt. Okay, there's going to be a 4 pi squared. This is the RPM value. So, RPM value squared into R squared by 3600. Where does that 4 pi squared come in? Because we are talking about angular velocities. 3600 comes in because usually centrifugal speeds are given in rotations per minute. But in SI, we have to do rotations, number of rotations per second. Okay? So if I have that, this is again gone. Let me dictate a problem to you. This is really, let me see if I can do something about this. Okay, can you see the problem? So consider a solution of proteins that are of mass 50 kilo DA is kilodaltons. So when you look at proteins or any biological complexes for that matter, whether it's a ribosome, whether it's a protein, nucleic acid complex, so on and so forth, the typical masses are provided in daltons. Okay. For all operational purposes, 1 dalton is roughly 1 gram per mole. It's approximately 1 gram per mole. I have put it in double. Okay. And typical proteins are measured in kilodaltons. Okay, there's a thumb rule, 1 kilodalton is roughly 10 amino acids. We use that as a back of the envelope thing, right? So if you tell me it's a 50 kilodalton protein, I'll say it was roughly 500, give or take a little. Roughly of the order of 500 amino acids. That is one detail you don't have to do. So consider a solution of proteins that are of mass 50 kilodalton. Usually people write it as kg. Let me make it bigger.
They consider it ये कम करो नीचे वो छोटा सा शक्ल है ना उसको बड़ा हो जाएगा हाँ वही मैंने बोला था नीचे
This protein solution is spun in a centrifuge. Okay? And it's a very weak, low power centrifuge. Okay? That achieves the highest rotation per minute of 100. Find the concentration ratio in the centrifuge at R equal to 0 and 5 centimeters away from the spinning axis at R equal to 5. How would you do that? You will go back to the previous equation. So note down this equation, which I have also written down there. This part. It's also written there. You can see it. The light is poor today. And then let's try this. Let's see what kind of numbers we get. By the way, why does this KBT come up all the time?
Ma'am, Boltzmann distribution.
Boltzmann distribution, absolutely. But KBT or RT, that's a measure of what?
Thermal energy.
That's a measure of thermal energy. And that is exactly what you are working against. Your diffusivity, your tendency to move. So if I did my spray bottle experiment on a cold day, where the temperature is 15 degrees, and I did it without the AC on a hot day, where the temperature is 40 degrees, the time at which you have to wait to get the equal scent on both sides will be different. If your thermal energy is more, it's going to travel faster, right? So that thermal energy, that KT that stands there, it gives you what you are working against. Okay? It kind of gives you the sense of the effective diffusion coefficient there, though D does not show up. So if I plug in all this, what will be the concentration ratio? So when I do CR by C0 and I get the right side, what do I have to do? Suppose I calculate the right side correctly. I need CR by C0. What do I need to do? I need to exponentiate. CR will be C0 e to the power something. Right? And in this case you will realize what we are trying to do is we are trying to get a higher concentration away. Okay, I want a higher concentration of my plasma proteins or whatever it is away from the tube. Okay, so if you work this out, I missed the 4 pi r square. That is something I realized. But what is CR by C0?
3 to the power.
Huh? Oh, yeah, I did put the temperature, no? 3, nothing is given, take it as 3, take it 0.6, take it as 310, 310 Kelvin is fine. No, 0.6 will be RT. See, there's one little trick here, please pay attention. Just stay here. So here, what is the molecular weight given in? Effectively grams per mole. Hence, should I use RT or kg? We can use RT, right? So this makes it a little convenient for you. I can easily use RT, which I know is 0.6, ballpark 0.6. And my mass is given in grams per mole, okay? Though I have to, if I want to stick to SI units, I should do it as kg per mole. 50 kilodaltons is 50 into 10 to the power 3 grams per mole. So it is 50 kilograms per mole. Kilo is 10 to the power 3. So 50 kilodalton is
50 kilograms.
50 kilograms per mole. Okay, so I use it in N. Okay, your RPM is given. Alright, you do your R square. There's a 4 pi square. You divide by 3600. While you're doing RP, please make it, if you're not clear, please think through this and get it calculated. And sometimes a little bit worried about you guys there. There are a lot of people clustered behind. You know, we have to apply everything to go into that side. Okay? But, you know, please just help. It's not hard. Right? So, I don't know, how can you guys even see from this?
अरे मास ऑफ प्रोटीन मतलब मास ऑफ वन मॉलिक्यूल ना इसका मतलब कैपिटल एम बाई एन ए कैपिटल एम में जो मतलब कैपिटल एम जो जो कैपिटल एम है उसको कितनी है और एन में नीचे
R is I said centimeters, so again you have to convert. So you have to do 5 into 10 to the power minus 2 square.
capital N is equal to
1.5. So CR is 1.5 times C0 is what you're
so
getting.
capital N ऊपर आ जाएगा N
1.
M N A by capital N
Only 10%.
तो वो N A R में
right?
जाएगा ऊपर वाला एनिमेशन
How much are you getting?
M divided by N R आएगा तो capital N कहाँ है वही मेरा डिवीजन वही तो डाउट है वो देखो अब पहले ही मास M मतलब क्या स्मॉल m मतलब क्या है वो मास ऑफ वन मॉलिक्यूल मास मोलर मास गिवन मास क्या है M अरे यहाँ पे क्या दिया
Somebody got 1.5. I think 1 point something is roughly the
1.00
1.00. So if you let's for a moment reflect on this. You can go back and do the calculations more correctly. But if I get 1.2, what does it mean? I'm only getting a 20% more concentration 5 centimeters away. That's probably not good enough. When you go and do your actual experiments, when you're trying to separate out the components, say within a cell, you need a high gradient in your concentration. What will you do? Clearly, this is a very bad centrifuge, right? This is only doing 100 RPM. A typical centrifuge that you will use in your bio lab is 50,000 RPM.
Low
There are
power
these ultra high centrifuges, which, if I'm not wrong, maybe Hassan can tell us, 300,000 RPM or something, 150,000 ultra high centrifuges.
Yeah.
There are these ultra centrifuges which can do 150,000 if I'm not wrong.
I saw 100,000.
100,000, 150,000 rotations per minute. So 100 rotations per minute is barely giving you anything. But just instead of in your RPM, just scale it up. Put 1,000, put 100,000 and see what you're getting. So if I really desire, if I'm designing an experiment, that will give me, say 1,000 times more concentration 5 centimeters away or 10 centimeters away. What kind of centrifuge do I need to use? So think of it as an experiment where you're working in a biology lab, okay, and you're working with a certain kind of cell type, and your advisor tells you to separate the components. Will you really go and run after an ultra centrifuge, or will a normal centrifuge work? How will you select the spin of the centrifuge, the rating of the centrifuge? Okay, we'll come back to one more example. I hope everybody knows about the ribosome, right? The machinery which spins your amino acid chains and all. You have the smaller unit and the larger unit. Okay? They are both of different masses. And one unit of specifying how big those are, we use Swedberg units. That is the amount of that is connected with
Sedimentation.
the centrifugation concept. We'll come to it later.
Ma'am,
Okay?
here the small m, what exactly small m is?
It's the mass of the protein. It's the mass of each
Mass of a molecule.
mass of a molecule.
So that will be molar mass divided by Avogadro number of molecules.
You can do that as well? Yeah? Alright, so we have to stop here, and I'm going to send you slightly refined slides because this got a little bit mixed up.